Hello, my name is Claudio, and in this video I will present the paper entitled Quotient of the Bruhat-Tits tree by function field analogs of the Hecke congruence subgroups. I will start by saying that classically in number theory we study the property of the integer numbers and extensions. In this way, we are interested in the group as the group gamma, defined as the group SL2 with integer coefficients. We can describe this group gamma by studying the action of this group on the Poincare half plane. Here an image of the Poincare half plane, and here an image of the fundamental domain defined from this action. By using this method, we can present gamma as the group generated by two elements that define these relations, where S and T are these matrices. By using this approach, we can also describe some congruent subgroup of gammas, for instance, the principal congruent subgroup, the group gamma 1, and the Hecke congruent subgroups. So I will say that this article is devoted to study a function field analogs of the Hecke congruent subgroups. For example, we can replace the integer number by the polynomial ring, and then we can describe the involved Hecke congruent subgroup. In order to formalize this idea, I will take a projective, smooth, geometrically integral curve defined or a finite field. I will denote by f the function field of c. Then we can take a closed point of the curve. We can define u as the open affine set defined as c minus p infinity. Then we can denote by R the ring of functions that are regular in U. For example, if we take the curve V1 and we take a point of degree 1, then we obtain a ring which is isomorphic to the polynomial ring. We can also take a more complicated curve, as for instance this elliptic curve, and for instance P infinity at this point at infinity, in order to obtain this quotient of the polynomial ring in two variables. So here we have our main objective, which is to study these Hecke congruent subgroups where A is an ideal. So our method is to replace the Poincare half plane by the Bruhat-Tits tree of SL2 of Kp, where Kp is the completion of Kp, and then here we can study the action of HA. Here we have an image of the Bruhat-Tits tree. So our goal is to describe the associated quotient graph. And then by using the Basser theory to present the Hecke congruent subgroup as an amalgamated product of simpler subgroups. So in the context of the polynomial ring, Jekyll was studied the preceding group, obtaining a variety very interesting results. Here we have a variety very interesting papers, and these articles contain important consequences for the informal form. So I will pass to our main results. We have that the quotient graph is the union of a finite graph with a finite number of rays called cusp. This is a classical result of Jean-Pierre Serre. The number of a non-relational family of cusp rays is called the cusp number of the quotient graph, and it is denoted as by Ca. So I will decompose the level ideal as a product of prime ideals with multiplicity, and then we can describe of first main results that state that the cost number is less than or equal to this constant, where phi is the maximal exponent to subgroup of the picard root of R. Moreover, we have equality when the preceding group is trivial and each multiplicity is odd. Here, an image of a quotient graph with the cusp in red and the finite graph in blue. So in the sequel, we can assume the good hypothesis in the preceding theorem, and then we can present the Hecke congruence subgroup as an amalgamated product of simpler subgroups, which heavily depends on the structure of the cuspidal rays. And finally, we can describe the abelianization of the Hecke congruence subgroup by saying that this is finite generated when each multiplicity is 1, and this is the product of a finitely generated group with an infinite dimensional FP vector space in any other case. Thank you very much.